Hi students! Today we're going to look at exponential equations and specifically how we can apply the laws of logarithms to solve exponential equations. Once we get practice solving exponential equations and logarithmic equations, we'll be able to use them to explore real-world applications. So let's start with exponential equations. An exponential equation is just an equation where the variable is inside an exponent. So for example, we have 2 to the x power equals 7. Now this would have been challenging for us to deal with before we had learned about logarithms, but now that we know a little bit about logarithms, we should be able to solve this very easily. There's actually 2 different methods we can use here. The first method is that we can rewrite this equation in logarithmic form. Remember that whenever we have an exponential equation, we can rearrange the numbers in it and write it in logarithmic form. So 2 to the x equals 7 is equivalent to log base 2 of 7 equals x. Remember, any exponential equation can be rearranged into a logarithm. So we've got log base 2 of 7 equals x. And if we want an exact answer, we can write x equals log base 2 of 7. However, if we're asked for an approximation, because we want to have an idea of what the value of this is approximately, we can use the change of base formula to rewrite this as log of 7 over log of 2, or even natural log of 7 over natural log of 2. Either way, it doesn't matter. When we use a calculator to get an approximate answer, we should get 2.807 either way. That's the first method that we can use, but there's a second method that we can use as well. We can take the log of both sides. Let me show you how this works. We have the equation 2 to the x equals 7, and we've solved equations before. We knew that there were certain things we could do to both sides of the equation to give an equivalent equation. Remember, we could add or subtract the same quantity on both sides, or we could multiply or divide both sides by the same non-zero quantity. Well, there's another property of equality that we're learning today. This says that if we have an equation, we can take the logarithm of both sides, and we end up with an equivalent equation. And it doesn't matter if we're doing a common logarithm or a natural logarithm or any other logarithm, it just requires that the bases are the same. So here I've taken the common logarithm of both sides, and the advantage that we have here now is that this exponent can come out front as a coefficient from one of the laws of logarithms. So we can rewrite this as x times log of 2 equals log of 7. And then to get x alone, we divide both sides by log of 2. So we get log of 7 over log of 2, which is exactly what we had earlier using the other method. And this is a fine final answer if we want an exact answer. But again, to get an approximation, we use a calculator, and we end up with 2.807. So either one of these methods should work when you're solving an exponential equation. I'm going to be primarily using the second method just to give students a consistent experience. You could use the first one if you prefer it, but I'm always going to use the second one just so that we're doing the same thing and getting practice over and over. Now I want to do 2 more examples right now, just so that we can get a little bit more practice. First, let's solve 3 to the x plus 2 equals 8. This is another example of an exponential equation because we have a variable inside the exponent. To solve this, I'm going to take the logarithm of both sides, and I'm actually going to take the natural logarithm instead of the common logarithm just to demonstrate that we can use either. So here we've got ln of 3 to the x plus 2 equals ln of 8. And we can take the exponent and bring it out front as a coefficient. So that gives us x plus 2 times ln of 3 equals ln of 8. Now we want to get the x alone. The first thing we can do is divide both sides by ln of 3. That gives us, and I'm going to write this over here, x plus 2 equals ln of 8 over ln of 3. I divided both sides by ln of 3. And then to get x alone, we can subtract 2. So that gives us ln of 8 over ln of 3 minus 2. And this is a perfectly good exact answer. But if we want an approximation, we can use a calculator to do that, and we end up with negative 0.107. All right, let's do one more. Let's solve 8e to the 2x equals 20. Now, one thing I want to do before I do anything else is I want to get this e to the 2x alone. So to get rid of the 8, I'm going to divide both sides of the equation by 8. This gives us e to the 2x equals 2.5. We could do 5 halves. I just went with 2.5. And then if we take the natural log of both sides, well, the natural log of e to the 2x is just going to be 2x. The reason why is because taking the natural log of something and raising e to that power are inverse functions or inverse operations. And so in the end, taking a natural log and raising e to a certain power cancel each other out, and we're left with 2x. Another way you could see that is by pulling 2x out front, and then ln of e is just 1, so you've got 2x times 1. Regardless, we've got 2x equals ln of 2.5. To get x alone, we can divide both sides by 2, so we end up with ln of 2.5 over 2, which is great for an exact answer. But we can use a calculator to get an approximation, and we end up with 0.458.